Mobility requires power, and I think we all agree that this power should more and more come from renewable energy sources. And new technologies are entering our daily lives more and more. Renewable energy is one example, autonomous vehicles, drones, and many others are other examples. And one of the buzzwords in industry has become digitalization. And what it means is that conventional analog or insular processes are replaced by fully digital workflows that can be connected and that can interact with each other. Now, the generation of electricity is undergoing a massive transformation. And as we all know, coal and oil are replaced with wind power, solar, or hydropower. And I think the reduction of the CO2 footprint is a common objective of most of us. Now, these new energy sources, while at the beginning they required subsidies from governments, they're now becoming more and more competitive due to the advances in technology. For example, just an example is if you look at the cost for new wind turbines, they have fallen more than 35% per megawatt over the past decade. And we think that now further gains in efficiency can be obtained by implementing digitalization strategies in operations and maintenance. Because we'll see operations and maintenance have at the beginning of this renewable energy journey have been neglected somewhat, and this is now changing. Looking at the global wind power, of course, wind and solar are the two fastest growing alternative energy sources currently. The global install base for wind power is even more than 650 gigawatts, and that means about 400,000 wind turbines are today in operation. And if we look at how they are distributed across the globe, we have kind of three clusters. One is the Americas, which is now growing or is expected to grow quite rapidly. This also has to do with the change of president in the US. The second cluster is Europe, where we see less growth because some of the in Germany, for example, most land that is suitable for wind parks has been used up. There is still growth in Scandinavia. And then there is a lot of growth in Asia, and China today is by far the largest single country in wind energy. What's also remarkable is how these turbines have evolved over time. When we look at 1990, the typical turbine had a power of half a megawatt, 500 kilowatts. And as they grow in size, of course, the power rating increases, but also the efficiency increases. And that's one of the main reasons that manufacturers are building larger and larger turbines. We're now at 10 megawatts per turbine. This is remarkable. And if you look at the comparison of the Eiffel Tower to a 10 megawatt turbine, you see that the tip actually surpasses the height of the Eiffel Tower. So these installations are enormous in size. What does it mean? It means that today there are about 1 million rotor blades in operation worldwide. And rotor blades are sensitive to environmental impact. And that's why we should really take care of them, and we should also monitor them. Now, a wind turbine consists of basically three components. There is a tower, there is the generator. The generator sits up in this housing on top of the tower, and the three blades. These are basically the main components of a wind turbine. Now, these blades, they're exposed to great dynamic mechanical stress. Just imagine that the tip speed of one of these blades is between 300 to 400 kilometers per hour. And these blades are in continuous operation 24 hours a day, 7 days a week over a 20-year period. And they're operating in, sometimes very harsh environments. Temperatures can reach from -40 to +50 Celsius. In some regions, there are abrasive particles in the air. If a turbine is located near a desert or even near a beach, we'll see a lot of abrasion through to particles in the air. And also the impact just of rain is very substantial. In the northern areas, we see ice forming on the blades, and sometimes these pieces of ice, they can be, dozens of kilograms, they fall off and they crash into the next blade that is turning, and it causes damage. Last but not least, there are thunderstorms and lightning strikes. And all these environmental phenomena can have a deteriorating impact on these blades. That's why we need to keep an eye on them. And just imagine the value of these blades. One of these blades can cost between 100,000 up to 1 million euros. So they're expensive. So again, why do we inspect rotor blades? That's important to understand. There's a whole number of reasons why we want to do that. First of all, we want to avoid blade failure because it's very, very costly to replace the blade. You don't only have to buy a blade, but you have to bring in a gigantic crane to replace the blades. And that by itself is an expensive proposition. Very important is we want to detect defects as early as possible. And let's take an example, a crack. A crack might start out as a very small 2 centimeter long crack, but they tend to grow over time. And if we let them grow too long, then the repair will be much more expensive than if we repair it very early in the game. Because there's different repair methods. One is just to send up a person inside of the tower and let them down along a rope. They can, do a hand repair, they call it, versus again bringing in a big mechanical structure to do a more extensive repair. Then also important is to identify, this sometimes happens, to identify manufacturing defects. This is particularly important during the warranty discussion. A normal wind turbine has a 5-year warranty period, and once that expires, of course, the owner wants to know, are there any damages that should still be covered under warranty? What is now becoming more important is to optimize intervention programs, because repairing blades is expensive. So we need to optimize it. We don't want to send a repair crew for every single damage we see one by one out in the field, but we have to cluster these together so that in one wash we can, repair several turbines. And I'll get back to that again later. We can also validate the quality of repairs. Some repairs are carried out very, very professionally versus others. There are some low cost service companies. They might do repairs that don't last very long. So we can also take a look if that's done right. And then oftentimes these parks are sold, and of course the new owner wants to exactly know what he buys. He wants to have full transparency with respect to the condition of the turbine and the blades. And then discussion with insurance companies also require inspection information, inspection data. In some countries, there is legislation in place that mandates inspections at certain given intervals. For example, in Germany, that's the case. And then, and this is what the industry is probably most excited about, is to really understand the propagation of these damages over time, because that's the basis to implement what's called predictive maintenance. And predictive maintenance is almost like a magic bullet for operations and maintenance, because it can really make a substantial contribution to further reducing the total cost of ownership. Last but not least, maintaining a mint condition of these turbines means simply more output. I'll give you an example. If we have significant erosion on a blade, this can reduce the energy output by up to 5%. And this is very substantial. So these are the reasons we're we're doing all this. The magnitude of the challenge is enormous. On the right side, you see a comparison between an A380 and one of these rotor blades. And now the newest rotor blades are even longer than that. They're exceeding 100 meters now. Towers exceeding 200 meters. And the surface of one of these blades is exceeding 500 square meters. That's basically the surface of 2 apartments. And you have to realize that on that surface, we're trying to find hairline cracks. And these inspections have to be carried out more and more now on an annual basis. And what does it mean? We have to inspect the surface far exceeding 50,000 football fields and document every hairline crack. To do this manually is literally impossible. Now, but how did they do it so far? There were 3 methods in place. One is the rope inspection. That's probably the most commonly known. It's a very manual, slow procedure. Again, a technician has to go up tower. Each tower has a slow moving elevator inside. It takes about 10 minutes to get to the top of the tower. Then they are taking ropes, and like mountain climbers, they go down along the blade, just visually looking for damages. And if they see a damage, they take out the pocket camera, digital pocket camera, and take an image. And then in the evening, they have to copy and paste together manually PDF reports from all this. So this is a tedious, dangerous, not reproducible process. This is the opposite of a digital process. Then the second method is to basically take a high power telescope and do it from the ground. This comes with other problems. With the increased size in turbines, the observation distances, they are getting bigger and bigger. And with that, the image quality is getting poorer and poorer. And they also require difficult turbine manipulations. You have to turn the blade to see it from the top to bottom, leading edge and trailing edge. So this has been very common, but it's now more and more replaced by drone inspection. And the last one is just for an example. There are also these platforms, mechanical, like a crane more or less, that bring people up to the blade. They're very expensive, and this only makes sense in the context of doing minor repairs. So all three methods are not satisfactory to do routine annual blade inspection at very high volumes. Now we're kind of flashing back a little bit to 2016. This was when after I had sold a startup in Silicon Valley. I was at the time tinkering around with autonomous vehicles. And Chris, a buddy of mine, he was deeply involved with drones in open source communities. They were developing flight controllers. This was still pretty early in the game. Drones are not all that old. And by coincidence, oftentimes, things happen by coincidence. Another colleague of ours calls us up from Denmark, and he says, "Hey guys, you're tinkering around with all this technology, and here is a big company, and it seems that they're really looking for a solution to inspect these rotor blades." Company was Vestas. It's today the world's largest manufacturer of wind turbines. And this triggered really the interest of Chris and myself, and we were starting to ask ourselves, is there maybe an opportunity to develop technology and but to really do it in a professional fashion so that we could eventually offer an industrial digital end-to-end process for these inspections. That's kind of how things started out in 2016. So we asked ourselves, what if we would use the latest technology to develop such a process? So, and by process, we meant an all digital end-to-end process. It would have to be cost effective. All these damages that we would find would have to be documented in a digital fashion. We wanted to produce actionable insights, of course, tell the owners and operators of these parks what are the necessary interventions given the inspection results or the inspection data that we generated. So it's like blade health information at your fingertips across, across a universe of wind turbines. And also regarding the insurance companies, the word transparency is very important, because you have to picture yourself being in the shoes of an insurance company. You have this large portfolio of wind turbines that you cover, but you have absolutely no clue what the condition of these turbines looks like. So creating transparency for us was very important. And also creating a lifetime documentation for these rotor blades. Like, every car has a service booklet, but this didn't exist yet for wind turbines. And of course, to deliver state-of-the-art image quality. And if we look at all the different technology that this touches on, then it's a whole basket of them, from cloud services, drones, of course, artificial intelligence. I'll talk about that a little bit more. Robotics, Internet of Things, big data, all these things come together when you want to put together such an industrial process. And that's challenging, but it's also very rewarding. So then we sat down and started to, pin down the requirements, because we knew that inspecting manually one of these turbines would take, on the rope, it would take half a day. And we wanted to bring that down to less than 1 hour, because when you have to stop the turbine, of course, you're not producing energy. And, this by itself would be a cost reduction, reducing the downtime of the turbine. For us, it was also no option to have any manual pilots flying around with these drones, because if you stand near one of these turbines, then only you realize how gigantic they are and how difficult it is to, for example, judge from the ground, or, at what altitude are you? Are you too close to the blade, too far from the blade? So manually piloting a drone was for us no option. The goal was clearly to document 100% of the blade surface. And, I remember being in a conference once where an operator of a wind park said, you drone guys, come back to me when you have image quality that allows us to count the legs of a fly on the blade. And everybody laughed, of course. And, we achieved that goal 2 years ago. So this is how fast things can move in this space. Then we also realized early in the game that an autonomous drone producing great images is only one part of the solution, because these drones, they accumulate such enormous amounts of data in short periods of time that you need a very powerful infrastructure behind it to process, to store, to manage all this data in a secure and trustworthy way. So the solution had to be scalable. Of course, our ambitions were not to only inspect, I think, the 37 turbines we have in Switzerland, but to do this on a global basis. And we, from the beginning, decided not to put together an army of field operators. These are the people who have to go basically from turbine to turbine and operate the drones. But we wanted to do this in partnership, because there are service companies that do work in the park, and we thought it would be most suitable to partner with them, given the technology, provide them with training, and then they could actually carry out those drone inspections in the field. What that meant, though, is that our system had to be monkey proof. And, monkey proofing a complex technology is very challenging. It's comparatively easy to make something work in a laboratory type environment. But if you then want to deploy it with technicians that, sometimes are maybe, not the ETH graduate style, then you have to have a system that is very easy and, easy to operate. And of course, the solution had to be rocketized. I mentioned before, the environmental conditions are extremely harsh. And of course, the drone solution has to be able to operate in these types of environments. And ultimately, we also said, and this thing, it has to make a contribution towards lowering the total cost of ownership. Now I want to show you. Now we kind of do fast forward, and I'll show you one of our recent videos that pretty much documents where we're at today. I hope you can see it. I think it should work.
Visual rotor blade inspections using autonomous drones hold great potential for owners and operators of wind turbines. With our 3DX blade platform, we provide an end-to-end solution for the full inspection process that is customizable to suit your needs. We work with local teams, so you can choose to do everything with us, do parts in-house or with a qualified third-party provider. Thanks to the browser-based online platform, inspection data can be processed and analyzed from anywhere in the world. Let's have a look at how it works. Our experienced team takes care of the detailed planning and management of the project. Thanks to the easy setup and user-friendly interface, you have full control over the inspection performance at all times. You can rely on high-quality image and metadata capture covering 100% of the blade using autonomous drones on predefined flight routes. The pilot training takes less than half a day, and the downtime per turbine is not more than 30 minutes. The image data is then securely uploaded to the cloud, ready for the annotation process. Thanks to AI-aided processing of the large number of images, the time invested by blade experts is minimized. Our intuitive work process and applications support teamwork, and annotations are easily reviewed, corrected and approved in our browser-based interface. Inspection reports can be generated and shared with your organization, end customer and repair teams, along with interactive links embedded in our applications and reports. Having all the information you need at your fingertips allows you to take decisions based on actionable insight, plan repairs, and budget O&M spending with higher precision. Book a demo with us today or find out more about our solution on sulzerschmid.com.
So thanks for bearing a little bit of marketing. So you can see that it looks very easy now, but it was not easy to get there. And I just want to kind of maybe share a few things that we encountered along the way. Now today we're actually in a position where it's great because now we have a system. It's battle tested. The autonomous drone is a very important key ingredient in the whole solution. Of course, now we're working on new things like making this fit for offshore inspections and many other things. Just to give you a glimpse at some of the numbers we have inspected. Meanwhile, we have inspected more than 7,000 turbines. I think this year we are active in 30 countries. All manufacturers are part of our portfolio. The downtime, as the video said, is 30 minutes, and we have identified more than 250,000 damages, and that's growing on a daily basis. And one team can do up to 17 inspections per turbine. Remember, that the old-fashioned way was maybe 2 a day. So it's enormous what this technology really can do. Now, to share just a few obstacles, because it's easy to say, oh yeah, this looks very easy, it's easy to use, and so the first thing we realized when we started out is that drones, they navigate by GPS localization data. And very quickly we realized, oh, this is not reliable. If you are very close to one of these rotor blades, it's like standing next to a gigantic wall. And that means that you're in the so-called GPS shadow. You can't see all the satellites that you want to see. And the trustworthiness of the localization of the GPS suffers. Then also these turbines, they some of them produce magnetic interference. Sorry, because in the generator there are gigantic magnets, uh, and drones don't like that. And then last but not least, there can be very significant turbulence near the blades. So these were some of the surprises we encountered. We had to mitigate all this. We're now using laser scanners to really scan the whole environment, including the turbine. And with this sensory information, we can dock onto the turbine in a very robust fashion. Then the environment, batteries are sensitive to hot and cold. So to make this industrial, we had to build battery heaters, battery coolers, special charging stations, things that at the beginning you would never think of. The aging of batteries is a problem. Then corrosion of electronic components. You would be surprised to see some of the cameras that we get back from the field, for example, in Texas. I mean, they're completely full of dust. Some others are, where we see a lot of corrosion. So these are other types of problems. And then the logistics also. Picture, there is a team out in West Texas. They sometimes don't even have a cell connection and they have a technical problem. They, of course, want to ask us, what do I need to do now? So these are other challenges that we have to overcome. And sometimes we have calls from teams. This happened last year in North Sweden, where the team says, it's all full of snow. Can you please organize a snow plow because we cannot get to the farm, to the wind farm. Then the data management. This is another big challenge, which is often underestimated. If you're dealing with terabytes and terabytes of data, you have to be very, very careful that that you assure data integrity. It's very easy to encounter data corruption or missing references and things like that. So that's very, very important. And then, of course, the data processing itself. Manually looking at these millions of images is not an option. So we early in the game, we engaged this. We did not all do ourselves, but in partnership to develop an AI solution, artificial intelligence solution, to detect anomalies in this image material. And that was a very important key ingredient in putting together the solution. And then, of course, all sorts of analytics reports in all shades of color and gray. And this all, when we started out with data capture with autonomous drones, and now we're really talking about an inspection platform with all these different components. The data capture is just like one aspect of the platform. A very key element, so this is something we're very proud of, is we call it the blade station. The blade station allows our customers to really access every square inch of their entire fleet, with a click of the button. They can just pull up a turbine, they can inspect the entire surface of the blade. Of course, they're mostly interested in looking at the damages, but and you can do this even in like time lapse. You can check, okay, how did this blade look last year? How does it look this year? What are the changes? Do we have any damages that changed in severity, for example? Did the crack grow or did the crack remain the same? These are things that we can now do with this type of data that we are collecting, and combining or leveraging this data with these kind of tools. And just to give you an idea, this AI solution was trained with I think with 150,000 annotations. You always need a training set to train the AI, and just to arrive at that was a monstrous challenge. And these tools, they turn more and more now into a collaborative platform, because you as a park owner, you might want to share this information with a service company who can directly quote to do the repair work. You just, send them a link. They can look at the same damage and they say, okay, the repair of this damage. Well, this damage that we see here is cannot be repaired anymore. But typically they can say, okay, this repair would cost you, 5,000 euros, for example. So it's like an ecosystem that starts to evolve. And of course, again, we can virtually walk around the blade. We can walk up and down the blade. Um, this is really a completely new world. And then the analytics style. I mentioned that one of the things we're excited about is to attract more and more knowledge from the data. I'll give you a few examples. For example, let's take erosion. As an operator or owner of wind parks, I'm, for example, very interested in knowing what's the magnitude of erosion that we have in our fleet, because I know that if we have a lot of erosion, the turbines are not producing at their maximum possible output. And with these tools, you have answers to all these questions, within seconds or minutes at the most. A very large customer asked us recently, or told us that they had seen problems with damages this was again in Finland, I believe, strange damages that they haven't seen before, and asked us if we could help them find out what was going on. And, it turned out that they had de-icing systems built into those blades. And what that basically is basically a heater that heats up the blade a little bit to melt the ice. And so it turned out that when when they turned on these de-icing systems, the ice would start to melt, but they put the turbine back into operation before all the ice fell down. And so as soon as they started to activate the turbine, the remaining ice was falling off, and it was always, crashing into the next blade that was following behind. And that can cause huge damage. And with the type of data here that we're collecting and the tools that we built, such questions can be answered rather quickly. And even more so now, we are starting to attach cost models to damages. And what that means is that now, pretty much at the push of a button, you can get a very clear understanding of the cost of the upcoming repairs that you have to, face for your assets. Not only that, but we can even tell you, it's going to be amount X within 3 months, and then, amount Y over 9 months, because you don't want to repair everything at once. We can bundle and cluster together certain repairs in a more optimal fashion. And this all really makes a contribution to making these renewable energy sources more competitive. And I think, drone technology, autonomous technology is one element, but all the other pieces that I mentioned before, from AI, big data, all this together can really have a very substantial impact. And if we, look even further into the future, I mean, this is, we are still convinced this is just the beginning of something, even bigger. And in our field, we see now that in large parks, we can imagine that we don't even need to bring the teams to the park anymore. We just install, we call them a resident drone that sits in, it's like a little doghouse for drones, where the drone waits and charges its batteries. And whenever there is a need for an inspection, the roof opens, the drone flies to the turbine, inspects the turbine, brings back the data, and goes back into the little doghouse. Those are, resident drones that would yet again help to reduce cost in larger parks, both onshore and offshore. And then also there are projects to create robots, and, mostly robots like crawling robots that attach to the blade that can do minor repair work. That's another arena where things are happening. Then offshore, we don't only want to inspect above the water, we also want to inspect the support structures below the water. So you can picture, you know, the submarine drone looking at corrosion and so forth. Then blade inspection inside. We are currently involved in a project where we want to take a close look at the blade from the inside because they're hollow. Now they sometimes even send people into the blade to see if there are cracks. And of course, this is also not a very pleasant assignment. We can we can picture drones flying into the blade or crawling into the blade to you know, to take care of that. Then new types of sensory equipment. Sometimes it's really interesting to take a look into the blade, and thermography allows us to do this to some degree, I would say. We can check if the bonds are okay, because oftentimes or sometimes the trailing edge just pops open because the two shell halves have not been glued together properly. And these are things that with thermography we can also detect early. And then other efforts, and this is becoming more and more important, deal more with standardization. We call this taxonomy because, you know, each company at the beginning started to create their own damage classification system. And of course, all these systems are incompatible with each other, and to find translation between them is sometimes very, very difficult. So now we're also involved in, you know, in some efforts to bring more standardization to this operation and management business for renewable energy. That was what I wanted to share with you in my presentation, and I hope you have many challenging questions.